We have reviewed the engineering stages: conceptual, basic, detailed. Let's now look at the different disciplines that are part of the engineering group in an industrial project. Within the general organization of the project, the engineering group is structured into different disciplines, each typically having intermediate managers to coordinate the specialists within the group. These intermediate managers are technically skilled individuals with extensive experience in their respective fields. As part of the engineering group, there is usually a general area known as project engineering. The role of a project engineer can be described as a link between the project manager and the technical disciplines. Their responsibilities include pre-planning and resource forecasting for engineering and other technical functions of the project. As with everything related to project management, these are typical examples, but the most appropriate organization and coordination approach will depend on each company and project. Let's now look at each of the technical disciplines within the engineering group. The process engineering discipline focuses on the design, operation, control, and optimization of chemical, physical, and biological processes. Process engineering spans a wide range of industries. This discipline carries out all calculations related to and required for the production process. Process design can involve new installations or the modification of existing ones. It begins at the conceptual level and, as we have seen, ends in the form of detailed construction plans. The documents issued by this discipline serve as the starting point for all the work of all other engineering groups in the project. It is important to note that process design, which is the responsibility of this discipline, is not the same as equipment design. In industrial projects, the process group is often internally organized as shown, with teams dedicated to conceptualization, calculation, diagramming or drawing or drafting, and quality assurance of deliverables. This structure can, of course, vary greatly depending on the nature and size of the project. As mentioned earlier, the documents issued by this discipline form the foundation of all other engineering activities. These key documents include, among many others, block diagrams, flow diagrams, piping and instrumentation diagrams, PNIDs, etc. If the process discipline stands out as the starting point for all other disciplines, the piping group has also a special role, coordinating all disciplines due to its responsibility for the veins and arteries of the entire industrial facility. This coordinating role requires piping engineers to have a general understanding of all other disciplines to facilitate interaction with each other. For example, this discipline is responsible for defining the spatial distribution of all major elements, equipment, structures, piping systems, etc. To do so, they must consider both the process requirements and characteristics and compliance with spacing criteria to ensure safe operation and maintenance of the plant. The piping discipline, led by its supervisor, is usually divided into four work groups, as shown in the following organization chart. Engineering development, piping layout, both 2D and 3D, stress and flexibility analysis, and quality assurance and control of deliverables. It goes without saying that the actual organization will depend on the complexity and scale of each project. As detailed in the study notes, the drawings, documents, models, and analysis tasks that fall under the direct responsibility of the piping group conform an extensive list. In addition, like most other disciplines, this field requires strong interaction and collaboration with other engineering groups through shared and jointly developed documents and models. As mentioned earlier, a piping engineer is not expected to understand reaction kinetics or the sizing of a safety valve. However, a basic understanding of the process is essential, since the fundamental concept of a plant is reflected in P&IDs, piping specifications, equipment data, instrument specifications, etc. Mechanical equipment is the discipline that applies engineering principles, physics, and material science to the design, analysis, manufacturing, and maintenance of mechanical systems, both static and rotating. It is one of the oldest and broadest engineering disciplines. This field requires a strong understanding of core concepts, including mechanics, thermodynamics, material science, and structural analysis. This group is typically organized according to the type of equipment, such as static equipment, rotating equipment, package units, and a team responsible for the quality assurance of deliverables. As mentioned earlier, this discipline materializes the concepts outlined by process engineering. Depending on the requirements, this may involve direct design or selecting a commercial piece of equipment that best fits the process needs. As with other disciplines, this group generates numerous documents throughout the project. Just as an example, these may include the design and calculation of static equipment, separators, tanks, heat exchangers, etc., layout drawings, many other related documents. Civil engineering is a discipline concerned with the design, construction, and maintenance of the built environment, including roads, bridges, metal structures, concrete structures, and project buildings. Its internal organizational chart typically differentiates between metallic and concrete structures. It also includes specialists in underground structures and other dedicated to structure layouts, both in 2D and 3D. This discipline also produces a wide variety of deliverables. This may include engineering for site preparation, designs, calculations, plans for metallic and concrete structures, underground systems, etc. Instrumentation is defined as the art and science of measuring and controlling process variables in a production or manufacturing area. The process variables used in industries include level, pressure, temperature, humidity, flow, pH, force, speed, etc. Control systems engineering is the discipline that applies control theory to design systems with desired behaviors. The instrumentation and control engineering discipline materializes the control required for each process. This involves designing and configuring control loops and selecting the necessary equipment. The technical knowledge areas within the instrumentation and control group typically include process control design, equipment selection, such as instruments, transmitters, etc., detailed design of control loops, and 2D and 3D layout of necessary cable trays and conduits. As mentioned earlier, some of the activities and deliverables of this discipline include developing control loops, selecting equipment and control systems, modeling control systems in intelligent simulation software, etc. Finally, the electrical engineering discipline is responsible for everything related to electricity generation, transmission, and distribution, as well as the design of various related equipment. In large projects, electricity is supplied to the site through high or medium voltage transmission lines. This group is typically divided by voltage level, separating medium and high voltage design and calculation from low voltage systems. Cable routing and distribution for different conductor sizes are handled by a separate team, as is quality assurance. Some examples of these disciplines' deliverables include design and calculation of high, medium, and low voltage systems, specification of electrical equipment such as transformer and protection systems, lighting system designs, short circuit current analysis, etc. We have seen the different engineering disciplines that are typically involved in an industrial project. The effective integration of these disciplines requires the use of specific software tools, project management skills, and clear proactive communication. Investing in interdisciplinary collaboration not only improves efficiency and safety in industrial projects, but also ensures their long-term sustainability in an increasingly demanding industrial context. In general terms, there are three key aspects in the interaction between disciplines. Collaborative design. Throughout the different engineering phases, the disciplines work together to create a coherent design. For example, the process and mechanical equipment groups interact to ensure that the equipment design properly meets the specifications of the production process. Interface management. Interfaces between disciplines such as the connection between piping and control systems or mechanical equipment require precise coordination to prevent errors and conflicts. Conflict resolution. Conflicts between disciplines often arise, such as spatial constraints between civil infrastructure and piping, which must be resolved through interdisciplinary coordination. The engineering team, as we have seen, consists of multiple disciplines. This fact creates factors that hinder effective communication and interaction. For example, differences in technical language. Each discipline has its own technical language and ways of representing information. This can lead to misunderstandings when sharing documents, drawings, or specifications. Interfaces. As mentioned, are points where two or more disciplines must collaborate. In the example figure, collaboration between mechanical equipment and piping is essential to ensure best technical solution at the connection point between pipe and tank. Lack of communication. This can lead to divergent technical solutions that, when viewed in isolation, may seem correct, but are mutually incompatible or inefficient. Discipline-specific objectives. These may not always align within the overall project goals. This can lead to conflicts over design decisions, schedules, or resource allocations. Soft skills gap. While engineers are experts in their technical fields, they often lack training in soft skills such as effective communication, negotiation, and teamwork. This can be a barrier to idea exchange and problem solving. Time pressure. The urgency to meet tight schedules may lead disciplines to work in isolation to speed up their portion of the project, neglecting interaction and coordination with other areas. Let's see some possible tools and solutions. Project management. It should promote interdisciplinary integration meetings aimed at aligning objectives and resolving technical conflicts. Cross-training. It should be among different disciplines and it fosters technical dialogue and empathy regarding each group's priorities and challenges. Integrated engineering products and software models serve as a powerful interaction tools, providing a common language across disciplines. Well-configured collaborative platforms enhance effective communication among different project stakeholders. Large organizations have standardized conflict resolution processes to streamline the search for solutions whenever necessary. In an industrial project, the generation and coordination of technical documents are essential to ensure that all participating disciplines work in alignment and without conflicts. Let's look at some of these key documents shared by multiple groups. Piping and instrumentation diagrams. The purpose of this document is to detail all the piping and instruments of various processes within a project. Process engineers are the responsible ones for this document. Piping uses P&IDs to design piping systems and select materials. Instrumentation and control defines control strategies based on the indicated instruments. Electrical engineers uses valve and sensors data for wiring and electrical systems design. Mechanical design drawings. They specify details of mechanical equipment, fluid transport systems, and connections between equipment. It is created by the mechanical equipment department. Civil verifies compatibility with structures and foundations. Process ensures that equipment meets processing requirements. Electrical coordinates power supply for mechanical equipment as needed. Civil and structural design drawings specify the design and foundations, buildings, structural supports, and drainage systems. As expected, civil and structural engineering is the group responsible for this type of documents, which are used by the mechanical equipment for the details on the equipment supports, electrical engineering for conduits and grounding systems, and piping to assess space requirements for major equipment. Similar multidisciplinary interaction can be seen in multiple other documents, such as single line diagrams and electrical plans, representing the distribution of electrical power, electrical control systems and protections. Control strategies aimed at the definition on how the process will be controlled and which automation systems will be implemented. Risk analysis and HACCP, which are documents prepared to identify and mitigate operational and safety risks in the project systems. All of this is just a partial sample of the multidisciplinary nature of many key documents managed under the responsibility of the engineering group.